So this week we're going to start really diving into hypothesis testing and inferential statistics. So for this chapter, chapter 8, we're going to talk about the process overall for how we do hypothesis testing in order to make claims about a population from a sample. So in order to do inferential statistics, scientists almost always use hypothesis testing as the basis to do such statistics. And what hypothesis testing is it's a method where we use our sample data to consider whether a certain hypothesis about a population is actually supported or not. And we use terms like supported as opposed to prove or demonstrate. And we'll see why in a bit, because it's all about probability, like we talked about last week. How probable is it that a sample data reflects the population that we think it comes from? So the logic of a hypothesis test kind of works like this. We state a couple hypotheses about a population. The sample is similar to the population, or this sample is not similar to the population. And based on those hypotheses, we define what we expect those to be. Are we saying that the difference between a sample mean and a population mean is a certain amount? That's along the lines there for that second bullet. And then from there we go on to collect a random sample of data and then do statistical analyses on that sample data. And if our results are consistent with our hypotheses, we can say that there's support for our hypothesis. But if they're different, we can reject a hypothesis. So what's important to know here is that the statistical procedures we use generally will do this, especially the ones you'll be learning this semester. We'll be able to reject a hypothesis or not reject a hypothesis based on our sample data. So before we go too much further in, I just want to review what we expect when we give someone a treatment or consider two different populations. So for an experimental design, we start out with this one population, we pull people from that and give them a treatment. If the treatment works, we expect them, as we talked about last chapter, to be different than this population after the treatment. So they'll be part of a new population where the mean will probably be something different. Generally, the standard deviations will stay the same. And this is essentially another look at that previous slide. We take our original population with a known population mean, pull a sample from it, and provide a treatment. And then we get data from our treated sample. And what we're expecting here is that at a population level, that this treatment has changed some of this population into this different population by giving them a new mean. So if we have a population of people with chronic depression, and they have a mean of 16 units of some random scale of depression, we would expect after their treatment that maybe this mean would be lower, maybe a mean of 10, which should be reflected here, if the treatment worked. So in hypothesis testing, we have 4 steps. First, we state our hypotheses. You'll typically set 2. We'll see that in a sec. And we set the criteria for what we want to decide on whether we're supporting these hypotheses or not. And then step 3 is we collect our data and compute our statistics. And then step 4, we make a decision based off what the statistics say comparing to our criteria for our hypotheses. So step 1, we state our hypotheses. It's important that we set 2. One is a null hypothesis, which we designate by H, the 0 subscript, and there's an alternative hypothesis, which is H with a 1 subscript. The null hypothesis says that the treatment has no effect, or if we're comparing two different groups, that they're not different from each other. There's no relationship, no change, no difference, that there's no effect of an independent variable on a dependent variable. Whereas the alternative hypothesis states the opposite, that there is a difference or a change or a certain relationship. If we have two different groups, we would say in an alternative hypothesis that one group is different from the other. And so when we want to make decisions about whether we would support the hypotheses or not before we collect our data, we have to consider what outcomes are likely if that null hypothesis is true versus those that are very unlikely if the null hypothesis is true. So if the null hypothesis is true, that means that either like the treatment had no effect, or there's no difference between the groups, or no changes occurred. If that is true, then we should figure out what mean or other level of a statistic would be very unlikely to get if that null hypothesis is true. And we do that by defining an alpha level. So alpha is a Greek symbol, and it's going to be our significance level, which defines the probability that a value used will be very unlikely. And we typically set that at a probability of 5%. And if we go back to our normal distributions of sample means, and we look at our critical regions, those extreme outlier areas, these here, these are very, very low probability values of potential sample means, assuming that our null hypothesis is true. And then these in the middle are the much higher probability values that would occur if the null hypothesis is true. And these boundaries are set by the alpha level we choose. So if we choose a 5% or 0.05 alpha level, then that would be represented by these. So you'd have 95% in this value range, and then 2.5% here, and 2.5% here. Excuse me. And so this would be our critical region for an alpha value of 0.05. Remember, we calculated last time these z's. We didn't calculate them, I just told you them. These z values, negative 1.96 and positive 1.96, will delineate that area between what is highly probable if the null hypothesis is true and what sample means are not very probable if the null hypothesis is true. So the idea is that if we get a sample and after giving them a treatment, their sample mean lies somewhere over here in the upper 2.5% or the bottom 2.5% of the distribution of sample means, then we could say it's so unlikely we would have gotten these that we could probably have support for the idea that that sample mean, or that sample, comes from a population that is now different, and that the null hypothesis probably isn't true. And then after we define what would be our rejection or supported criteria, we collect our data. The proper way to do it is to collect your data after you've stated your hypotheses and established your decision-making criteria. And it just assures that we are objective in our science practice. And then we get our data and we calculate our sample statistics. So we compute, let's say, a z-score using our sample mean minus the population mean that we originally got our data from, and then the standard error, which is the standard deviation of the distribution of sample means. And so if that z statistic is located in one of the critical regions, which means it's either greater than positive 1.96 or less than negative 1.96 z-score, then we can say our null hypothesis is rejected. We can't say that we prove the alternative hypothesis, but we get to say that the null hypothesis is rejected. But if the z statistic is not located in those critical outlier regions, then we fail to reject the null hypothesis. We don't prove the null hypothesis, we just fail to reject it. This terminology is important. We make decisions about the null hypothesis in terms of rejecting or not, and we can't make statements about the alternative hypothesis. The only way we can say something about the alternative hypothesis is that because we've rejected the null hypothesis, all we can do is provide support for the concept that the alternative hypothesis is true. So to give sort of an analogy for what hypothesis testing looks like in a context you might be more familiar with, let's talk about a jury trial in a court of law. So when defendants go into court, they provide a plea of not guilty, typically. And the whole system assumes that a defendant is innocent until proven guilty. So we start with this null hypothesis that the defendant is not guilty. And then police and prosecutors, they gather evidence relevant to that innocent plea, such as any sort of evidence like videos, if it was a particularly egregious murder, any sort of blood, other pieces of evidence that they would use to establish support for or against this null hypothesis. And then at some point, they get sufficient evidence that demonstrates that with this evidence, this null hypothesis can't be true. And then they claim that the defendant is guilty. But if there's not sufficient evidence against this null hypothesis, the jury then fails to convict. That a court of law never concludes, though, that a defendant is innocent. They just say not guilty. And that's what's important. The important analogy here is we don't say that in a court of law that the defendant is innocent. We just say that the defendant is not guilty. And that is very closely aligned with what we do in hypothesis testing. We never say that we've proven a null hypothesis. But we can say that either we fail to reject or reject a null hypothesis. So the important thing about hypothesis testing is that we're not perfect at doing it because inferential processes use limited information from a sample to make a conclusion. And what's difficult about this is that errors are possible. We can reject a null hypothesis when we shouldn't have, or fail to reject a null hypothesis when we ought to have. So we have two different types of errors that can occur. So one is a type 1 error. And essentially this is that we reject a null hypothesis when that null hypothesis is actually true. Which means that, let's say a researcher concludes that a treatment does have an effect when it actually, in real life, doesn't have one. And this occurs sometimes. And so we could also say that if we have two different groups that we're comparing to each other, like one classroom and another classroom, a type 1 error would be we say that they are different in some way, that they have different scores on tests, saying that they are different, have differential capabilities, when actually they might not have any differences. And so these two bullets really get to the point of what a type 1 error is. There's what we find from our statistical test and what is reality that we don't necessarily get to test totally completely. And the probability that a test will lead to a type 1 error when the null hypothesis is true is the value of our alpha level. So if we chose an alpha of 0.05 or 5%, that 5% is the probability that our statistical test will lead to a type 1 error, given that the null hypothesis is true. And why is this a big problem? Because it's false reporting when we report our research. Essentially what that means is we've demonstrated, hey, this treatment works. And then we give it to clinicians to provide to patients, we market it, but we'd be pushing a treatment that actually doesn't work, and that just by chance we got a sample that appeared to show that it worked, when really we just got a very different sample by chance. The next type of error that could occur is a type 2 error. And this is where a researcher does not reject the null hypothesis when the null hypothesis is actually false. So this would appear as a researcher failed to detect a treatment effect. And oftentimes it comes up as a small effect that happened by chance, which in the real world and in other samples and such would show a slightly bigger effect. And so the probability that a type 2 error could occur isn't as easily identified as a type 1 error, which would be our alpha level. There's actually some complex calculations behind what we call beta. And I'm not going to ask you to do that for this semester. So this is just a table that shows the researcher's decision in a statistical hypothesis test versus what actually exists. Because sometimes our sample doesn't get close enough to reality. We just sometimes by chance can get samples that are a bit off of reality. And so if in the real world the null hypothesis that there's no effect is true, if we fail to reject the null hypothesis, then we've come to the right decision. But if we've rejected the null hypothesis, we've made a type 1 error. And if an effect actually exists for a treatment, showing that the null hypothesis is false in the real world, if we reject the null hypothesis, we've made the correct decision. But if we fail to reject the null hypothesis, we've made a type 2 error. All right, so that's just the basis for the kind of errors that you can see in a statistical test. This next slide here just shows some of the boundaries that we have in critical regions using z-scores. So for an alpha value of 0.05, the z-scores would be between negative 1.96 and positive 1.96. For an alpha of 0.01, negative 2.58 to positive 2.58. And for an alpha of 0.001, it's negative 3.30 to positive 3.30. Excuse me. And so just to summarize again, for the basis of hypothesis testing, our first step is we state our hypotheses and select an alpha level, and then we decide on our critical region what would be the values that we would define whether a hypothesis is supported or not. And then we collect our data and compute our test statistic, which in this case is the z-score, and we'll have plenty of others throughout the rest of the semester. And then we make a probability-based decision at the end about the null hypothesis. If the test statistic is unlikely, assuming the null hypothesis is true, then we would have a significant or statistically significant result, which would lead us to reject that null hypothesis. So there are a few things that can influence the outcome of a hypothesis test when we use z-scores. So a lot of these involve understanding what is involved with the z-score when we consider a distribution of sample means. What's important is that it all counts for the standard error of the mean. So size of the difference between sample mean and the original population mean. So if there's a larger discrepancy, you're going to get a larger z-score. This should make sense, that a larger z-score leading to a higher likelihood of rejecting a null hypothesis. But also, the variability of the scores matter. So if the variability in our population is much larger, then what you would see is the standard error of the mean being smaller in size, or excuse me, being larger in size. So you'd have more variability, larger standard error, and lead to a lower z-score, making it less likely to detect the null hypothesis being false. So the last one is the number of scores in the sample. Now, larger n means that we have a smaller standard error. So that decreases, this decrease leads to smaller z-score. So a few different assumptions that we need to think of, just to keep in mind, that we have random sampling, that observations are independent, which means that one sample is not related, one score is not dependent upon another. You don't have to worry too much about that. And that the value of sigma is not changed by the treatment. This is an important one, in that it assumes that regardless of what treatment is given, it doesn't influence how variable the scores are before and after the treatment. And then our sampling distribution needs to be normal, because that helps us to actually get to the appropriate critical region. So sometimes you might want to do, instead of the two-tailed test where we had in our normal distribution of sample means, where we had the lower end of extreme values and higher end of extreme values, we call that a two-tailed test. Sometimes we might not want to do just that. Sometimes we may have a specific prediction about the direction of the treatment, that the treatment should lead to a much lower mean or a much higher mean. When we have a specific direction, we can say it in the hypotheses. And that we can say that in the alternative hypothesis that there's an increase or decrease in the population mean, not just that it's different. So that would look like this. Instead of having both tails as a critical region, we would say just one tail has a 0.05 probability critical region. And so what a one-tailed test allows is to reject a null hypothesis, provided that the difference is in the direction that we predicted. This allows for a much smaller z-score. You see that we don't use 1.96 anymore. We can use 1.65 for an alpha value of 0.05. So we don't need as large of a z-score. But when we use a t-test, a two-tailed test, then we need a larger z-score. We need to get to 1.96, positive or negative. So in general, we're going to keep using two-tailed tests, because sometimes it's hard to come up with a strong enough justification based on theory to use a one-direction prediction. Okay, so this is it for the basis of hypothesis testing. So for the rest of this chapter, we're going to go a little bit into one more thing, actually two more things, that are important about hypothesis testing. And the problem is that in hypothesis testing, we only really focus on whether a null hypothesis is rejected or not rejected. But we don't know anything with that about effect size. How different are is the sample from our population mean or a sample from another sample? And so the problem with that is that we may get a statistically significant result, but it might not be that big of a deal. And it's often influenced by our n value. If we have a super large n, a super small effect may appear to be significant. So what's important is that we also test effect size, which is the magnitude of a treatment effect. And we do that through Cohen's d. So essentially what we do is we get the difference between the population mean of the treatment group and the population mean for the group that was prior to the treatment or didn't receive a treatment. And then we divide that by the standard deviation of the population. Not the standard error, it's the standard deviation, because we're assuming that the standard deviation of the population has stayed the same before and after treatment. And so if this value is a magnitude of 0.2, we consider it a small effect. And this could be positive or negative. Remember, it's magnitude. We're not considering sign. So the treatment mean could be smaller than the no treatment mean. So if it's negative 0.2, we would include it here too. So if it reaches 0.2 to 0.5, we say it has a small effect. So if it's 0.3, it would be small effect. Between 0.5 and 0.8 is a medium effect. And if it's greater than 0.8 magnitude, we say it has a large effect. If it's less than 0.2, so if it's 0 to 0.2, we would say that it has a negligible effect. And the standard deviation here is important to consider, because what if you have two different situations where this difference between these means is the same? Well, what makes that difference large? Well, it's the standard deviation. If your standard deviation is super large, then such a difference between two groups wouldn't be as large as compared to if the standard deviation was quite small, comparatively. So if the standard deviation is fairly small, a difference, a certain amount, will look fairly big. And you'll get much larger Cohen's d. All right, so lastly, we're going to talk a bit about statistical power. So the power of a test is the probability that a test will correctly reject a false null hypothesis. So power is our ability to determine whether we would detect a treatment effect if one is assumed to exist. And the calculation for power is 1 minus beta, where we talked about beta being the probability of a type 2 error. We usually will calculate these before starting a study. And it's a very complex calculation, and so you don't need to worry about doing it for this class. But I may give you a beta on a quiz and tell you to calculate power, which would be a fairly easy calculation. The complexity of calculating power just comes from this beta. And we have a few influences on power as well. So if it's a super large effect size in reality, our power will be fairly high. And also larger sample sizes will produce greater power because it's just as close to the population size as possible. And using a one-tailed test will increase power relative to a two-tailed test. So you would decrease power by reducing the alpha level. So instead of 0.05, let's say we use 0.01, we've made the statistical test more stringent, giving us lower power. And then if we were to switch from a one-tailed test to a two-tailed test, we would decrease power because two-tailed requires larger z-scores to prove a statistically significant result. All right, that's all for Chapter 8. You're going to have Chapter 9 this week as well. And if you have any questions, please stop by office hours or get in touch with me. As this is where the material starts to get much more difficult in terms of theoretical concerns and such. So if you are having any issues, please reach out.